Okay, let's go ahead and get started. So today what I would like to do is complete our review of the subject of quantum kinematics. So first, just a question. Did you guys all enjoy the lecture on last Friday? Yeah. It's pretty interesting. He talked about Boltzmann brains?
Yeah.
Okay, pretty cool stuff. Much more prosaic stuff today. So today I would like to finish our lightning review of quantum kinematics and move on to discuss the problem of quantization, observables, and so forth. So just to set the stage and remind you of where we left off last time I lectured. So states, in physical states of systems in quantum mechanics are represented by rays in a Hilbert space. This Hilbert space is an finite or infinite dimensional complex vector space on which we can do calculus, integrate, differentiate, and so forth. We can consider operators acting on this Hilbert space, and observables are Hermitian operators which act on this Hilbert space. So I just remind you that this Hilbert space comes equipped with the notion of what it means to talk about a dual element of the Hilbert space. So for every ket vector in our Hilbert space, we can define the corresponding dual. There is an inner product which allows you to combine a bra and a ket in order to make a complex number. And this gives us a notion of a Hermitian conjugate, so that if you have an operator A acting on a ket, then this in general will not be equal to the dual of A acting on the ket from the right as opposed to the left. And so because of that, we define the Hermitian conjugate so that A dagger alpha is the dual of A acting on a ket alpha. And an observable is a Hermitian operator in the sense that A is equal to A dagger, and in fact these two things are equal. And the important point is that, one of the important points is that the eigenvalues of a Hermitian operator are real. And moreover, one of the basic postulates of quantum mechanics is that the eigenstates of a Hermitian operator, and in particular of an observable, form a complete basis of our Hilbert space. So what does that mean? That means that any state alpha, which in your Hilbert space can be expanded as a linear combination of the various eigenstates, which I've called an here, of some operator. So here we're summing over all of the eigenvectors of an operator A, so that A acting on one of these states, an, is just a number, usually denoted an, on the state an. This is one of these extremely slick notations where we use the operator, the notation A in 10 different ways to mean 10 slightly different things. But by working with some examples, you'll probably hopefully realize that this is an extremely slick and useful notation. So one way of summarizing this relationship is that the operator 1, which is the operator that doesn't do anything to states in your Hilbert space, is the sum over n, an, an. So this is one of the most important formulas in quantum mechanics. A useful life lesson is that many wonderful things can be thought of learned by thinking of 1 and writing the number 1 or the operator 1 in as complicated a way as possible. So here we learned that by thinking of the identity operator as the sum of all possible projection operators onto a basis of your Hilbert space, you can learn interesting things. So, for example, it is this writing which gives us a notion of a wave function. So far, we've thought of states as being described by some abstract objects that we called kets that live in a Hilbert space. And the expansion coefficients of this ket in a particular basis associated with an operator are known as the wave function. So an alpha is called the wave function of the state alpha in the basis associated with an observable A. So, for example, if you consider a particle moving in one dimension, then you could describe this particle in terms of the variables x and p, which become operators in the quantization of the system. And then you could write down a basis of eigenstates associated with the operator x. So the operator x hat acting on one of these eigenstates will just be a number, x acting on the eigenstate. So the state x here is the state where the particle is in a definite position x. And then an arbitrary state psi can be expanded in this basis using the fact that 1 is equal to the sum over x of the projection operator onto the basis element x. And then this quantity here is nothing more or less than what we usually call the wave function psi of x. And likewise, if you were to expand the dual of psi, then that would be the integral dx of x of the bra vector x times the inner product of psi and the ket x. And using the rules for the inner product of a Hilbert space, this is the complex conjugate of the wave function psi of x. So often in an initial treatment of quantum mechanics, you start by thinking about wave functions and only later organize your thinking in terms of abstract Hilbert spaces. But that way of approaching things often obscures a lot of the basic physics, because one of the crucial aspects of quantum mechanics is that you can use whatever basis you like in order to make the problem at hand easy to solve. So, for example, some problems might be easy to solve in a position space basis, other problems might be easy to solve in a momentum space basis, and other problems might be easier to solve in some combination thereof. In general, the trick and the art of solving problems in quantum mechanics involves choosing a basis which is adapted to the symmetries of the problem at hand. And so as we continue in this class, we'll again and again see examples where in order to solve a problem efficiently, one just has to choose the correct basis where the problem becomes elementary. Okay, so what sort of operators could we define acting on this Hilbert space? So this is a Hilbert space which, if you wanted to think of it, could be thought of as a space of square integrable wave functions. So one natural operator that we can define well, there's the x operator, of course. So what is x acting on a state psi? Well, you just insert 1 equals to the integral dx of the projection operator. And what do you get? Well, because this state here is an eigenstate of the operator x, I guess if I wanted to be particularly pedantic, I could put a little hat here so that we remember that it's an operator. we'll often be a little lazy and neglect the hats when everything is clear. So x hat acting on this eigenstate is just the number x. So we get the integral dx of x times the wave function psi of x. Or, so what are we saying here? What we're saying here is that the operator x takes the wave function and multiplies it by the function x. So the operator x takes the wave function psi of x and multiplies it by x. Right? That's all this equation is saying. But it's often helpful to think about this in a slightly more abstract Hilbert space language, as I have done up above. Okay, so what other operators could you imagine? Well, we have a function of x. One thing you could imagine doing is differentiating that function. So we could define the derivative operator, which is just defined as the integral dx of the x derivative of the wave function. So at this point, this is just some definition that you could give for an operator acting on this Hilbert space. And you could then ask questions. Yes?
The derivative operator is the derivative with respect to x, right?
That's correct.
Okay, but should we put del x or...
Yeah, if you wanted to be very precise, I could write this as d by dx. Okay. So far, I'm considering just a particle moving in one dimension x, so there's only one possible derivative I could define. I don't have to worry about d by dy or d by dz. So I'm using a sort of abbreviated notation where I was leaving out a lot of the details. But yes, if you wanted to be precise, you could call it d by dx.
What about, for example, d by dt, for example?
Yeah, one could also define that operator. Yes, I've been, one could also define that operator, but that's not the operator I'm talking about. So, good. Okay, so what sort of properties does this derivative operator obey? Well, let's look at this expression here. So, let's take, for example, the inner product of some other state with the derivative operator acting on psi. So what is that? That's the integral dx of the wave function chi of x times the derivative of psi of x. Sorry, this is the wave function chi of x star. So chi of x star. So one thing that you could do is you could integrate this by parts, and you would get a boundary term minus the integral of the derivative of the wave of chi star, so d by dx chi star. So let me just write that as chi star of x times psi of x. So then, plus a boundary term. So if we're thinking about square integrable functions which vanish at x goes to infinity, because the integral of their square is a finite number, and the only way that could be finite is if they vanish, then this boundary term will be equal to 0. Now, of course, one could try and define another Hilbert space where there are boundary terms, and indeed, such Hilbert spaces are often very useful for solving certain quantum mechanics problems. But in the simplest case, where you're talking about a space of square integrable wave functions, that boundary term is equal to 0. So let's stare at this expression here. Well, what is that expression? That is just minus the complex conjugate of psi times the derivative operator acting on chi. Right? You just take this guy, switch chi and psi, and then complex conjugate it, and you'll get precisely this expression that I've written in the second line there. And what is that? Well, that is by definition minus chi times the adjoint of the derivative operator acting on psi. So what have we seen here? What we've seen is that the derivative operator is anti-Hermitian. I suppose last time I only defined a Hermitian operator as one that is equal to its adjoint. An anti-Hermitian operator is one which is equal to minus its adjoint. So that means that if you define the operator I times d by dx, that is a Hermitian operator. So that is a great candidate for the momentum operator. There's one thing that you need to remember, however, which is that we need to write down an equation for the momentum operator that is consistent with dimensional analysis. So x has dimensions of length, d by dx has dimensions of 1 over length. So that means that you need to put some constant in there which has the appropriate dimensions if you wish to identify this as momentum. So let's just put a constant in there. I'll call that constant minus h bar. And this then is a Hermitian operator, which is a good candidate for the momentum operator. And indeed, as expected, x and p will obey the standard Dirac canonical commutation relation. Any questions before I continue? Yeah. No questions? Okay. So this was just an example to illustrate some of the concepts that we described last class involving Hilbert spaces, linear algebra, and so forth. I would like to remind you also of a few basic facts involving observables. So an observable is an operator which is Hermitian and one of the postulates of quantum mechanics says that if A, the observable, is measured in a state psi, then if we were to, so if we were to measure an observable A, then the outcome of an observation is an eigenvalue of A, and the probability of observing a particular eigenvalue is equal to the square of the overlap between the eigenstate A and the state psi where you're performing the measurement. And here, in writing this formula, I'm normalizing everything, so I'm taking psi to have unit norm, and I'm taking A here to be an eigenstate with eigenvalue little a, which is also unit normalized. So then you could ask, what is the expectation value of the observable A in this state? Well, that is just defined as the overlap of psi with a psi. And my claim is that this is the expected value of A given this postulate up above for the probability of observing the outcome of an experiment in quantum mechanics. So to see why this is true, all we need to do is remember that 1 is equal to the sum of the projection operators onto A. So let's just insert a 1 here and insert a 1 there, and what do you get? Well, you get a sum over n of psi an times an AM, where we're also summing over M because we're inserting 2 ones of the projection operator onto AM. And using the fact that AN and AM are eigenvalues of A, this guy will be equal to AN times the overlap AN, AM. So if we just choose an orthonormal basis where AN squared, so the norm of AN, the state AN is equal to 1, and the overlap between AN and AM is equal to 0 if N is not equal to M, then this is just the sum over N, AN times the absolute value of AN with psi. Or just the sum over N, AN times the probability of observing AN. So what I'm saying here is something that is rather elementary, which is that the expected value, if the probability of observing an eigenvalue A is the overlap of psi with A squared, then the expected value of the observable A is the sum over all of those probabilities times the value of A. And indeed, using our usual rules in quantum mechanics, that is nothing more, nothing less than the overlap of the wave function psi with A times psi. Any questions on that? So we verified that this definition of the expectation value of A is exactly what you would say it is using the usual principles of statistics. Okay, so just a couple more definitions. So 2 observables, A and B, are said to be compatible if their commutator is equal to 0. And in this case, the observables can be simultaneously diagonalized. And in fact, it's an easy exercise, which I encourage you to work out if it's not clear, that any observables which can be simultaneously diagonalized necessarily commute. So the statement that they're simultaneously diagonalized means that one can take a basis for H, so one can find a basis for H such that if you take the operator A and act it on one of the basis elements, you get a number, and if you take the operator B and act it on one of the basis elements, you also get a number. So is it clear that if 2 operators can be simultaneously diagonalized, their commutator must be equal to 0? If that's not clear, think about it, and try and prove it to yourself. So this lecture today is a fair amount of review. So if you're bored, prove that to yourself, and if you're still bored, prove it again. So 2 observables which do not commute are referred to as incompatible. And all of the interesting effects of quantum mechanics come from the consideration of incompatible observables. In particular, the most important such effect is the uncertainty relation. So what is the uncertainty relation? So let's define the variance of an operator as follows. So if I have an observable A, then I can define delta A as the operator which is A minus the number which is the expectation value of A. Or if you want to be extremely precise, it's A minus the number which is the expectation value of A times 1. then the expectation value of delta A squared is known as the variance. And that is, well, it's the expectation value of the quantity A squared minus the expectation value of A quantity squared. So this is the usual definition of variance in statistics. If you have some quantity A that you're measuring in some statistical sense, so you're measuring it lots of time and collecting statistics, then the variance of that variable is the expectation value of the square of that variable as compared to the expectation value of that variable, quantity squared. So, for example, you should convince yourself that if you're in a state where A has a definite value, then its variance is equal to 0. Okay, so let's all be quiet for a second and contemplate that fact. If you're in a state where A has a definite value, then the variance of A is equal to 0. That's practically the definition of variance. So what is the uncertainty relationship? So the uncertainty relation is the statement that the expectation value, or rather the variance of an observable A, times the variance of another observable B is greater than or equal to the expectation value of their commutator. So if A and B are Hermitian operators, then their commutator is an anti-Hermitian operator. I guess I haven't proven that to you, but it's a straightforward thing to prove, and we'll prove it in the course of proving this uncertainty relation. And then the expectation value of that anti-Hermitian operator squared is a number which sets a fundamental lower bound on the variance of A times the variance of B. So, have you guys all seen the proof of this before? Yes. Would you like me to prove it? No. Would anyone like me to prove it? Okay. The proof is an exercise. You guys have seen the Schwartz inequality? Yes. Has anyone not seen the Schwartz inequality? Don't be shy. Should I go through the proof very quickly? No. Yeah. Or of the uncertainty relation. No? Okay. I'll skip the proof. Okay. The proof is an exercise. It's actually not a very easy exercise. I feel a little guilty skipping it. Are you absolving me of my guilt? Yes. Okay, good. Just I'm a good Catholic, so actually I'm not a good Catholic. Okay, good. So the proof of this is an exercise. So this is a proof. This is a fact that is true in any state whatsoever. And so a state which has the special property that it saturates this bound for a pair of operators A and B has some sort of special status and is referred to as a minimum uncertainty state. So a state which has the variance of A times the variance of B greater than or equal to, saturating this bound, so equal to 1/4 times the commutator, is referred to as a minimum uncertainty state for the operators A and B. So now, if A and B commute, then what are the minimum uncertainty states? This is a puzzle. Okay. Anyone awake? What are the minimum uncertainty states if A and B commute? The minimum uncertainty states if A and B commute are just the simultaneous eigenstates. More interesting, however, is if A and B do not commute. So let's consider the case of a particle in one dimension. So in that case, the most familiar form of the uncertainty relation comes from the consideration of the position of the momentum operators, which do not commute, and therefore their variance, if you just go ahead and plug into this formula, is bounded below by the Heisenberg. So this is the Heisenberg uncertainty relation, that the expectation value of delta x squared times the expectation value of delta p squared is greater than or equal to h bar squared over 4. So you could then ask what the minimum uncertainty states are for the one-dimensional particle that we've been considering. Well, I will just tell you the answer. All of the minimum uncertainty states take the form of the exponential of a Gaussian, possibly with some momentum. So the Gaussian states you may remember as the ground states of the harmonic oscillator. So a Gaussian e to the minus x squared over d squared is the ground state of a harmonic oscillator. And if you just take a ground state of the harmonic oscillator, then that actually has minimum uncertainty, as we'll check in a second. And indeed, one can also just boost it, if you like, by giving it some momentum, and that state will also have minimum uncertainty. And if we wanted to normalize this state appropriately, then I would have to put some constant out front. What is that constant? Well, you need to take this guy and you need to square its absolute value and integrate dx. So you're integrating a Gaussian dx, which by dimensional analysis goes like root d squared d. So you need to put a 1 over root d there in order to get this to be unit normalized. And then there's some stupid constant. It's like the square root of pi. You could figure that out if you wanted to. So times some number. Okay, so let's just go ahead very quickly and check that this is a minimum uncertainty state. So what is the expectation value of x in this state? Well, this will be the integral minus infinity to infinity of x times e to the minus x squared over 2d squared, because the e to the ikx will cancel out when you take the absolute value. It's just a pure phase. So what is that? Well, that's equal to 0 by symmetry, because you're integrating an odd function of x dx. So that guy's easy. What is the expectation value of x squared? Well, that's the integral minus infinity to infinity of x squared times e to the minus x squared over 2d squared. How do we compute that integral? Well, we compute it by dimensional analysis. Okay. This is an integral dx of x squared, so I could figure out the d dependence just by rescaling x by a factor of d. Then that x squared will rescale by a factor of d squared. So you get an answer which is d squared. Okay. Times some number. The nice thing about teaching an advanced class like this is I never have to calculate any constants of order 1. It makes my life very easy. What is the expectation value of the momentum operator? Well, the momentum operator is I times the derivative operator. The derivative operator gives you ik plus a term linear in x. Okay, so what is this? This is the integral minus infinity to infinity of the I times the derivative of this Gaussian. What is that? Well, that'll give you ik plus something that goes like x over d squared integrated with this Gaussian, with some other factor of I, maybe a minus I here. Well, this term integrates to 0 because it's the integral of an odd function, and this term integrates to, k. So the expectation value of p will be h bar times k. P is minus I h bar times the derivative operator. And finally, the expectation value of p squared, well, you need to take two derivatives now, so that's minus I h bar, integral minus infinity to infinity. What do you get? Well, you end up getting, you can just take two derivatives of this Gaussian here. You get one term that looks like k squared, plus another term where the derivative hits this term here, which is a 1 over d squared, integrated with this Gaussian, plus a bunch of other stuff that integrates to 0 for the same reasons that we've discussed. So what is this? This is h bar I'm sorry. There's an h bar squared here. Good. This is h bar squared times k squared plus h bar squared over d squared. So if you put that all together, you see that the variance of x is some number times d squared. The variance of p, well, that's the expectation value of p squared minus the expectation value of p squared. There's a very pregnant pause in that sentence. So that's h bar squared over d squared, again, times some number. So that means that the product is some number times h bar squared. And if you want to be very careful, I challenge you to compute that number and show that it's equal to 1/4. So what is the significance of these minimum uncertainty states? So these minimum uncertainty states are the closest that one can get to classical states in quantum mechanics. So they're the closest analog of classical states where a particle has a definite position and momentum in quantum mechanics. So for this reason, whenever you're considering the classical limit of a quantum system, if, for example, you wish to understand you're working in an approximation, which is usually the important approximation where h bar is very small, and you only wish to understand the small deviations from classical physics due to quantum mechanics, then it will very often be useful to use the minimum uncertainty states as your basis of wave functions. So in particular, one can actually show that the states described above form a basis for the Hilbert space of a one-dimensional particle. Okay, up to a subtlety. Can anyone guess what that subtlety is? So, in particular, the states described above are not the most general form for a coherent state in quantum mechanics. Can anyone guess what the most general form for a coherent state of a one-dimensional system is? Okay, here. This is a fun challenge. Let's see if you're paying attention. So this is a minimum uncertainty state for a one-dimensional system. Can anyone figure out a way of generalizing that somehow and getting something which is guaranteed to remain a minimum uncertainty state? Have you had your Wheaties this morning? I can wait a very long time. The question is, can anyone figure out a way to generalize this, which will still remain a minimum uncertainty state? I'll give you a hint. Not every state has the expectation value of x equals to 0. That means that this is a Gaussian centered around 0. So that means if you want to find a more general form of a minimum uncertainty state, what you need to do is construct the Gaussian centered around some other point. What do you do then? Well, you just replace this x here by x minus x naught, where x naught is then the place the Gaussian is going to be centered around. And in fact, it's a true statement, one that I won't prove to you now, but I might prove to you later, that this set of states where you have Gaussians centered around all of the points on the line, dressed by this angular momentum e to the ikx, this forms, this is the most general form for a minimum uncertainty state in one dimension. And in fact, they form a very convenient basis. Why? Because this is the basis which is most closely analogous to the classical basis of states, where you describe a particle as having a definite position x naught and a definite momentum k. So the Gaussians centered at x naught with momentum k are a convenient basis so one could call those states x naught and k. It's important to remember here that this is not a state which is a simultaneous eigenstate of x and p. Okay. So there's no rule that says that you have to take as your basis the simultaneous eigenstates of some operator. For some other problems, it might be useful to take another basis of states. And so this is a basis that one could consider. Question?
Is this Gaussian basis orthonormal?
Absolutely. Okay, why don't you answer the question for me? The question was, is this Gaussian basis orthonormal? Here's a hint. Take the case where k is equal to 0. Compute the overlap between two Gaussians. Is it 0? No. That means that this is not an orthonormal basis. So it is not orthonormal, and it's also not any eigenstates of any convenient observable. But it's still useful. Why is it useful? Well, it's useful because there's a precise sense in which we've seen this is the closest to a classical state with position x and momentum k that you can construct in quantum mechanics. Question?
Does that mean that it's always possible to find that basis? Always possible to find those states that actually minimum frequency for
Yes. There are always minimum uncertainty states for a pair of operators that you would consider. How would you go about deriving the minimum uncertainty states? Well, you write down the definition of a minimum uncertainty state, and you regard that as a differential equation for your wave function. And then you solve that differential equation. Indeed, I challenge you to prove, so I'm handing out a problem set today. This is not one of the problems, but you should do it if you wish to please the great physicist in the sky. It's easy enough to prove to yourself that these are all the minimum uncertainty states. These states also have another name. These are referred to as the so-called coherent states of the one-dimensional system, of a one-dimensional particle. When we discuss quantum dynamics and the harmonic oscillator, we'll see that, in fact, as you can probably already guess, given that the Gaussian is the ground state of a harmonic oscillator, these have a very elegant description in terms of a harmonic oscillator. And as we know, physics is that subset of human experience that can be described by coupled harmonic oscillators. So that means that these are very important states. Yes, question?
Sorry, I'm confused about The states above form a basis for H.
The states above, yes. If I take, let me say these. Let's just say that the minimum uncertainty states form a basis for the Hilbert space. You have to include the Gaussian centered at other points.
Okay, so
Yeah.
like the Gaussian that you gave centered at.
The Gaussians centered at the origin do not form a complete basis for your Hilbert space. Prove that if it's not clear. It's not trivial. And then if you want to have a complete basis, then you need to take Gaussian centered everywhere. You know, these coherent states, when we revisit the harmonic oscillator, probably next week at some point, we will describe these in a much greater detail. There's a very elegant way of thinking about these. In fact, these coherent states and the closely related squeeze states appear all the time in various quantum systems. They appear in optics, they appear in cosmology, they appear in quantum field theory. So we'll revisit these, don't worry. Other questions? Okay, let's continue with our lightning review of linear algebra. So we've encountered, question? No, just a yawn.
Actually,
Yeah.
so in these things that you have to do the index 0, if I only consider the one that is in the center, so the only the case.
Yes.
Why is not a complete case? Because you said before that any revision operator,
Yes.
that well, all the vectors of this much
These minimum uncertainty states are not the eigenstates of a Hermitian operator. They're actually the eigenstates of an operator that is not Hermitian.
Are they vectors of B?
Oh yeah. They're an overcomplete basis. Okay. Let's put it this way. You're right. They're an overcomplete basis. You could always set d equals to 0, then you would get the momentum states. Yeah, which do form a basis. So they're an overcomplete basis. The ones with k equals 0, the Gaussians, are not centered at the origin. Those do not form a basis. Yeah. Good. Thank you.
By overcomplete, you mean they're not all linearly independent?
They're not all linearly independent. And for a general wave function, there are many different ways of writing it as a superposition of these states. So good, thank you. Sorry, I said something that wasn't technically correct. Other questions? Thank you. This is what happens when my graduate students sit in on my class. Okay, so we've encountered Hermitian operators. So a unitary operator is a slightly different beast. So a unitary operator is a linear operator which preserves the inner product between a vector and a dual vector. So in particular, if you have some operator u such that if you take u and act on a state alpha and then take the inner product with the state u acting on beta, or the dual of u acting on beta, which is beta times u dagger, so u and beta u dagger have an inner product which is equal to the original inner product of beta and alpha. So if you have a ket alpha and a ket beta, you act on both of them with u, then their inner product will be unchanged. So this implies that u dagger times u is equal to 1. Because if you have an operator whose expectation value in all states is equal to 1, then that operator is equal to 1. And likewise, it's easy enough to show that if u times u dagger is equal to 1, then u dagger times u is equal to 1, and vice versa. So in particular, and this is a fact, which, well, we could prove it if you like, which is that given two sets of orthonormal bases, let's call them A's and B's. So you could, for example, have the A's be the basis of eigenstates of some observable, and the B's be a basis of eigenstates of a different observable. Then there exists a unitary operator such that it transforms the A's into the B's. Does anyone want to construct that unitary operator for me? Okay, this is a homework exercise. Oh, yeah, okay. Exactly. This unitary operator, what do? You just project onto the BNs. And then you can show that u dagger u is equal to 1 using the orthonormality relationship. Conversely, if you take an orthonormal basis and you act on that orthonormal basis with a unitary operator, you'll find another orthonormal basis. So in your study of vector spaces in linear algebra or mechanics, you probably have encountered a rotation operator. So what is a rotation operator? A rotation operator is a matrix which, if you act on a basis of a vector space, preserves the dot product between vectors. That's just another way of saying that it preserves the orthonormality of some coordinate system. And these unitary operators should be viewed as the complex version of a rotation matrix. So it's the version of a rotation matrix relevant for Hilbert spaces, which are complex vector spaces. So two Hermitian operators A and B, which are related by a conjugation by a unitary operator, so A is u dagger bu, are said to be unitarily related. And they will have the same spectrum. Two operators related by conjugation by a unitary operator will necessarily have the same eigenvalues. The eigenvectors won't be the same, because the eigenvectors will be related by the action of this unitary operator, but their eigenvalues will be the same. Sometimes we'll say that they are isospectral. That's just a fancy way of saying their eigenvalues are the same. The number and the degeneracy of the eigenvalues is the same. A spectrum is just a fancy word for the list of the eigenvalues and the degeneracies of the eigenvalues of an operator. So likewise, one can define the notion of an anti-unitary operator. So an anti-unitary operator is an antilinear operator which has the following property. So that if you take, so let's call this operator theta, such that if alpha goes to theta times alpha, let's call that alpha tilde, and beta goes to theta times beta, which we'll call beta tilde, then the operator theta is anti-unitary if the inner product between beta and alpha is the complex conjugate of the inner product between beta and alpha. Sorry, if the inner product between beta tilde and alpha tilde is the, okay, let me start that sentence again. The operator theta is anti-unitary if when you transform alpha and beta, you get the complex conjugate of the inner product between alpha and beta. I remind you that an anti-linear operator is one where if you act the operator on I times some state, you get minus I times that operator acting on the state. Unitary operators you are probably familiar with. Anti-unitary operators you are not. But when we study symmetries in quantum mechanics, anti-unitary operators will be important. And in particular, it is a very deep fact that anti-unitary and unitary operators in quantum mechanics are symmetry operations. So classically, a symmetry of a system is a transformation of the variables of the system. So if you have some dynamical variables Q, which transform into some other dynamical variables, capital Q, then that is a symmetry if they leave, this transformation leaves the equations of motion unchanged. For example, a translation operator, x to x plus a constant, leaves the equations of motion of Newtonian mechanics unchanged because the equations of motion of Newtonian mechanics involve only the second derivative of x. That's another way of saying that the laws of physics shouldn't depend on, if I take a laboratory and I move it all 10 feet to the left, then the laws of physics as measured by that laboratory won't change. So in quantum mechanics, if I can spell mechanics correctly, a symmetry is a unitary or anti-unitary operator which commutes with the Hamiltonian. Now, we've so far just discussed kinematics. I haven't told you about Hamiltonians yet, but you, of course, know what they are. And indeed, in quantum mechanics, it is the unitary operator, which is the quantum mechanical equivalent of the canonical transformation that is the form of a symmetry in classical mechanics. So if you have a quantum mechanical system with a Hilbert space, then it behooves you to investigate the possible unitary operators and anti-unitary operators that one can construct which commute with the Hamiltonian. Because doing so will always make your life easier, because that will tell you the symmetries which will help you in solving that problem and in understanding the dynamics of that system. Indeed, the way that physics works from a practical point of view is often the opposite. Generally speaking, our strategy as physicists is usually not to try and guess the Hamiltonian, but instead to try and guess the symmetries that are relevant for a given physics problem, and then construct the most general Hamiltonian consistent with those symmetries. This is the underlying strategy in all of condensed matter physics and in particle physics. You start with some postulates for the symmetries of a system that are relevant for whatever regime you're trying to study, and then you write down some dynamics which is consistent with those symmetries. And this is an idea which we will return to again and again in this class. I think it's not too much of an overstatement to say that the study of physics is the study of symmetries. So this has been a bit of a lightning review of quantum kinematics. I suspect that it's either been too fast or too slow for most of you. Probably a little too slow. So I thought I would end by telling you something that you probably don't know. Okay. So thought I would like to end by just giving you a little bit of a taste of the theory of quantization, in as much as that theory exists. So let me just remind you that, as we have discussed, the space of states of a classical system is referred to as the phase space of the system. So the set of positions and conjugate momenta. And observables are just functions of points in space, phase space. So an observable is just a function of the positions and conjugate momenta. To quantize this system, we seek a Hilbert space and a set of operators. Let's call them A hat, such that the Poisson bracket, so the Poisson bracket between these classical variables, is transformed into the commutator of the quantum mechanical variables, the quantum mechanical operators, times a factor of IH bar. And the important thing, which they never teach you in your undergraduate classes on quantum mechanics, is that this procedure is not unique. So I just want to remind you that in classical physics, one can always choose a different set of variables, let's call them big Qi and big Pj, to describe phase space. You know, if you're talking about the motion of a pendulum, then you could either use the angle of the pendulum relative to vertical as your dynamical variable, or you could use the height of the pendulum off of the floor as your dynamical variable. And one of the basic principles of physics is that the result of any physical measurement shouldn't depend on the variables that you use to describe the system. So how do we describe this mathematically and precisely in classical physics? Well, what we need is to demand that these variables Qi and Pj have the same Poisson bracket as the original variables little qi and little pj. So in classical physics, we're always allowed to change our variables. So to take little q to some big Q, that's a function of q and p, and little p to big P, which is a function of q and p. And provided we choose our new variables to satisfy the same fundamental relationship that their Poisson bracket is equal to either 1 or 0, then that should give you a completely identical description of the classical physics. So this change of variables, which preserves the canonical Poisson bracket, is known as a canonical transformation. Okay, So now we need to ask the following question. If you choose one particular set of dynamical variables, little q and little p, and you quantize in such a way that you get the fundamental Dirac commutation relation for little q and little p, would that give you the same answer as if you chose a different set of variables, big Q and big P, and then quantized in such a way that you had the fundamental Dirac commutation relation for big Q and big P? So does the quantization procedure depend on which variables we choose when we quantize this system? And the answer is yes. What does that mean? That means that so when we specify a system in classical physics, that is not enough information for us to determine the corresponding quantum mechanics. So, in your junior level quantum class, you probably said, well, if you have a particle in some potential, you just, construct some wave functions and write down some Schrodinger equation, and that gives you some unique Hilbert space and some dynamics. But in fact, you were secretly making a choice when you did that. You were secretly choosing which variables you were going to quantize when you did that. And it's a confusing fact about quantum mechanics that this procedure of going from a classical to a quantum mechanical system is not a unique one. Now, nobody guaranteed you that it had to be a unique one. The real world is not described by classical physics. The real world is described by quantum mechanics. And it is the case if you have a given quantum mechanical system, there's a unique classical system you can get out of that by sending h bar to 0. But the inverse is not true. So if you started thinking that, well, life is classical physics and then we just need to come up with some quantum system that reduces down to this in some appropriate h bar going to 0 limit, then you would be confused because you would not be able to make unique predictions for the outcomes of certain experiments. There's just some additional piece of the dynamics that appears in quantum mechanics. There's a question over here.
Yes, so I'm just confused about what you mean by quantization procedure. Like, is it just going to operators? Like just putting paths and like...
That's an excellent question. So what do I mean by a quantization procedure? What I mean by a quantization procedure is an attempt to find operators such that, so what is quantization? So quantization is the attempt to find operators A and B, so some operators A hat for each observable A, such that the commutator of two observables is equal to the classical Poisson bracket of those guys plus some correction terms that are of order h bar squared. And it's these correction terms that lead to the problem of quantization. So the problem of quantization is what I have been describing, namely that for a given classical system, there's not necessarily a unique quantum mechanical system. And in particular, what that means is that it's simply not the case that one can compute, given a classical system, the commutators of all the corresponding objects, the commutators of all the corresponding observables. So what you need then is a procedure to compute these terms of order h bar squared. So let me talk about a very simple example. So consider a particle in one dimension. With some variables x and p. So then, classically, the observable x times p is indistinguishable from p times x. However, if you just did the naive quantization procedure, where you replaced xp times x hat times p hat, then this is not equal to p hat times x hat. However, life gets a little easier if we remember a rule that observables need to be Hermitian operators. And in fact, x hat times p hat is not Hermitian, nor is p hat times x hat. X and p are individually Hermitian, but remember when you take the Hermitian conjugate, you reverse the order of the operators. So we need to remember that x hat times p hat adjoint is p hat times x hat. So what does that mean? That means that there is a unique linear combination of x hat and p hat, of x hat times p hat and p hat times x hat, which is Hermitian. And of course, we need observables for Hermitian because the outcome of observations need to be real numbers. You know, if you calculate the expectation value of position times momentum, that better be a real number. So that means that the correct quantization principle will take xp and take it to 1/2 x hat p hat plus p hat x hat. So this is referred to as the symmetrization principle. And in fact, it is simply a true statement that, for example, the Poisson bracket of symmetrized operators does not agree, or sorry, how should I say this? Let me say this a little differently. The symmetrization of the operators may have commutators which disagree with the Poisson brackets by terms of order h bar squared or higher. So the simplest example is, so it turns out that if you look at the operator xp and you compute its Poisson brackets with x and p, then that will in fact equal the commutators of the symmetrized operator. But you could consider an operator like x squared times p squared, which is nonlinear. Then when you quantize, you'll get 1/2 x hat squared p hat squared plus p hat squared x hat squared. And it's a straightforward exercise to check, just using the canonical commutation relations between x and p, that the commutator of x hat squared p hat squared plus p hat squared x hat squared with x, say, is equal to I h bar times the Poisson bracket of those same operators, so x squared p squared with x, plus a term of order h bar squared, which you will compute on the problem set I'm handing out in a few minutes. And I think it's very important to emphasize that this effect is observable. And it's something that, in fact, you have already encountered in your elementary classes on quantum mechanics if you study the hydrogen atom. So, for example, consider the angular momentum operator, x cross p. Then you can compute the square of the angular momentum operator, just the square of that vector, which is x squared p squared minus x dot p squared. So this is the operator x squared p squared. So you have the same operator ordering ambiguity that I was describing above for the one-dimensional system. So what that means is that when you quantize this, j squared will go not to x squared p squared minus x dot p squared, but it will rather go to the symmetrized version of this, so x hat squared p hat squared plus p hat squared x hat squared minus x dot p as an operator squared minus the reverse ordered combination. And this is just not the same as the original quantity, as the original classical momentum. Indeed, the commutator of x and p is a constant. So if you work it out, this will differ from the classical expression by a constant. So you'll get x hat squared p hat squared minus x hat dot p hat squared plus a constant. What is that constant? Well, I won't bother and compute it for you. I'll just tell you the answer. By dimensional analysis, you know it has to go like h bar squared, because j has units of h bar. H bar has units of angular momentum. And so there's just some number, which is 3h bar squared over 2. And if you actually look back and think carefully about the hydrogen atom, this is something that you've already observed. So if you look at the ground state of a hydrogen atom, you might think that this is a state with no angular momentum, because angular momentum adds energy. However, if you calculate the expectation value of the angular momentum squared for the ground state of a hydrogen atom, it's non-zero. What is it? Well, it's 3h bar squared over 2. So, in fact, this operator ordering ambiguity and the fact that in order to get a Hermitian operator, you need to symmetrize is something that is not just observable, it's something that you've already seen in your quantum classes. Now, it turns out that for the simple sorts of system that we will be studying in this class, there is no problem of quantization, because there's this principle of symmetrization which allows you to uniquely determine a set of operators and uniquely determine their commutation relations. So you can completely uniquely determine all of these terms of order h bar squared that appear in the commutation relation. However, for systems more complicated than, say, particles moving in 3 dimensions, for example, there is no unique way, in general, to determine these order h bar squared terms. So in order to have a unique way of determining them, you just need to have some additional input when you define your quantum theory. And in fact, there's a mathematical characterization of which classical theories do have a unique quantization and which ones do not. That's not something that I think would be appropriate to discuss in this class, but it's a very interesting and important area of physics. So maybe I should stop here and see if there are any questions. How many of you actually saw the Wiles symmetrization principle in your previous quantum mechanics classes? You didn't see it. It's not something they teach. Okay, there was a question?
Just a point of clarification. So there's no unique way just because of the nature of...
Yes. Yeah. So it's just, if you think, what do we mean when we say we quantize a system? We start with some classical data like a Lagrangian and some phase space that the Lagrangian determines the dynamics on that phase space. The question is, can you go from that to a Hilbert space and a Hamiltonian? And the answer is sometimes yes, sometimes not uniquely. Okay. The characterization of which systems you can uniquely find the quantum system for is sort of beyond the scope of this class. But I wanted to introduce this to you. Lest you think that quantum mechanics is not sufficiently mysterious. You're at the point where you're now hitting real current research. I mean, this is something that people still work on and people are still confused about. Quantum mechanics is a living subject. Okay. It may be that by the time you are teaching this class in 10 years or 20 years, this problem will be solved. Any other questions? Okay, I'll see you on Friday. Oh, and there's a problem set here. Pick up a problem set. Due next Tuesday.